Welcome to all of our guests at today's educational webinar, PFAS in Drinking Water, What is the Risk to Your Health? I'm Melissa Scanlon, and I hold the Line B E-Line Endowed Chair in Water Policy at the School of Freshwater Sciences and direct the Center for Water Policy. Our center's mission is to connect the best research in water science, social science, and economics to inform policy that protects, restores, and conserves fresh water. One way we do that is by sponsoring a water policy scholar each academic year to conduct research and share that through educational events just like this one. We open an annual contest to faculty members throughout the UW system and fund one lucky scholar who is working to advance our understanding of water policy in one of the 10 grand challenges identified by the Freshwater Collaborative of Wisconsin. Today, you'll be hearing from our center's 2022-2023 water policy scholar and her team about the work they've been doing to assess human health risk from exposure to PFAS in drinking water. PFAS are harmful chemicals that are being found in many of Wisconsin's drinking water supplies and water supplies across the nation. These chemicals can cause problems in our organs, hormones, development, and can even lead to reproductive complications. So today we will hear about Dr. Suppes' study that assesses how dangerous it is for people to drink water contaminated with PFAS. The research she's done centers on people in Eau Claire, Wisconsin, but ultimately provides a risk assessment tool that other communities may also use. So as you listen to her presentation, please post your questions in the Q&A box, and we are going to discuss as many as possible after the lecture. Let me turn now to introduce today's speakers. Dr. Laura Suppes is an associate professor in public health and environmental studies at the University of Wisconsin-Eau Claire. And as I mentioned, is our 2022-23 water policy scholar at the Center for Water Policy. She received her MPH in public health administration and policy from the University of Minnesota and a PhD in environmental health sciences from the University of Arizona. Her research interests are chemical and biological hazard identification and remediation in water, exposure assessment, and quantitative microbiological risk assessment. She's joined today by one of her students who's worked on this team, Alex Barker, who is a candidate for the Bachelor of Science in Environmental Public Health at UW-Eau Claire. You can see the rest of her team up on the screen there. Camille Tilden, who is also pursuing a Bachelor of Science at UW-Eau Claire, and Sydney Morgan, who is getting a Master of Science in Environmental Engineering at UW-Milwaukee. So with that, I'm going to turn it over to Dr. Suppes.
All right, thank you so much, Melissa. Can everyone see my screen here? Seen some head nods, great. Well, thank you all so much for being here this morning. As Melissa mentioned, my name is Dr. Laura Suppes, and I'm Associate Professor at the University of Wisconsin-Eau Claire in the Department of Public Health and Environmental Studies. And joining me as a presenter today is my student, Alex Barker, and other students on the team were Camille Tilden and Sydney Morgan. And this research started, and I guess the idea for it emerged following the discovery of PFAS compounds in the groundwater below the well field, where the city of Eau Claire is drawing its water to serve to the community from the municipal water source. So that discovery drew a lot of media attention and a lot of questions from the public about their health and the safety of the water that they were consuming. And we wanted to answer some of those questions. So this study attempts to answer some questions that people are wondering about their exposure to PFAS through drinking water. So the objectives of this study were to assess the risk of adverse health outcomes from PFAS exposure in drinking water. So to do that, we created a model and we inserted that model into an Excel spreadsheet that is user-friendly. So it's meant to be used by the public or by decision-making groups. And it assesses or calculates relative risk of adverse health effects from exposures to PFAS in Eau Claire, Wisconsin, but also in other areas of Wisconsin or other areas of the nation. So we wanted to make it flexible so that anyone could use this tool or the Excel spreadsheet to calculate their risk and see if they are at risk of adverse health effects. So what exactly are PFAS? So it's not just one chemical. So when we say PFAS, we're actually talking about a broad category of chemicals, and it stands for per and polyfluoroalkyl substances. And these substances have been used in a lot of commercial and industrial products because they are resistant to water, heat, and oil. So they're very useful, but unfortunately, they are very persistent. So have been coined forever chemicals because they last in the environment, they persist in the environment for a long time once they're there. So we're finding them in our drinking water, we're finding them in soil, we're finding them in our environment. They also have been manufactured in the United States since the 1940s. So many have been phased out, but we're still using some today. And just that longevity has led to some environmental contamination. So from a public health perspective, we are worried about PFAS substances because of both cancer effects and also non-cancer health effects. So I wanted to include a list of non-cancer health effects because we typically just tend to think about cancer effects associated with PFAS, but this risk assessment actually only assesses risk of non-cancer health effects from PFAS. So things like organ dysfunction or hormone disruption, thyroid alterations, and developmental effects to fetuses like low birth weight, miscarriage, and growth delays. And unfortunately, the list kind of goes on. So even at very low concentrations, we are finding that some PFAS substances affect animal health and also human health. Here's a figure that shows some of the different commercial and industrial products that contain or have contained PFAS in the past. So many of us are using these every day, if not quite frequently. Things like cosmetic products, pizza boxes, paints, and dental floss, even nonstick cookware, waterproof clothing, candy wrappers, shampoo, pesticides, firefighting foam. So these substances have been included in a lot of different products that we're using. So I mentioned that this study began, or the idea for this study began when there are PFAS that were discovered in the groundwater in Eau Claire, Wisconsin. And that is where the city of Eau Claire draws the community's drinking water source. So here I have a map of Wisconsin that shows where Eau Claire is and a bird's eye view of where the well field is. And that is where the city is pumping up the water, they're treating it, and they're sending it out to the community for consumption. So the wells are located here. And if you go just to the right and uphill, you'll notice that the airport in Eau Claire is right here. It's just speculation at this point, and it hasn't been confirmed, but the thought is that the PFAS that is present in the well water, the groundwater here, came from firefighting foam that was used at the airport at one point in time. So that firefighting foam mixed with runoff, and then it infiltrated into the ground and it migrated into the groundwater here. So I'm going to show a timeline of events. This all kind of started in February 2019 when the U.S. Environmental Protection Agency released a PFAS action plan. So the U.S. EPA recognized that we were finding PFAS in the environment. There were a lot of knowledge gaps, so there wasn't a lot of toxicity information, which is necessary for assessing human health risks and determining maximum contaminant levels. And there was a lack of information on how to mitigate some of these environmental contamination events. So the action plan was released. In response to that, the Wisconsin Department of Natural Resources released a statement of scope declaring that they were going to eventually create some enforcement limits or maximum contaminant levels for some PFAS compounds in drinking water. And the Wisconsin Department of Natural Resources works with the Wisconsin Department of Health Services to determine what those concentrations should be. So after August 2019, in November 2020, the Wisconsin Department of Health Services came up with some recommended enforcement standards. So they decided that a mix of 4 common PFAS compounds should not exceed 20 parts per trillion. And then there were some other limits for 12 other PFAS compounds ranging from 30 to 450,000 parts per trillion. At that time, the city of Eau Claire tested the drinking water, and I'll be saying finished water throughout this presentation. What I mean by that is the water that's been pumped up from the ground from the wells, been sent through treatment, and is going to be distributed to a water tower or to people's homes in the Eau Claire area. So at that time, the finished water in June 2020, after these WDHS recommendations were released, the PFAS levels in the finished water in Eau Claire did not exceed those WDHS standards. The city of Eau Claire tested the water again, and this time they tested water coming from the individual wells. So there are 16 wells in that well field, and they found that 4 of the 16 wells did have PFAS at levels that were above those WDHS recommended standards. So they immediately shut down those wells. But the finished water, so because there's that dilution, the water is being pumped up from those wells and then it goes to treatment and all that water is being added together, there actually weren't any PFAS that were exceeded in the finished water at that time relative to those WDHS recommended standards. So since July 2021, and actually since June 2020, the city of Eau Claire has been monitoring their finished water for 19 PFAS compounds. And again, they have not found any PFAS compounds that have exceeded those WDHS enforcement limits. So during that time also, and more recently, the Wisconsin Department of Natural Resources announced that they established some maximum contaminant levels for PFOA and PFOS, so 2 different PFAS substances. And those substances cannot exceed 20 or 70 parts per trillion individually or combined. More recently, the United States Environmental Protection Agency in March 2023 announced that they're planning to add 6 PFAS compounds to the National Primary Drinking Water Regulation List. And this is a list of compounds where the EPA has maximum contaminant levels and municipalities have to abide by this and they can't exceed those levels. So for PFOA and PFOS, the potential, the newly proposed limit will be 4 parts per trillion by the EPA, which is obviously much less than this limit that was established by the Wisconsin Department of Natural Resources. So we'll see where that goes. Okay, so I'm going to kind of take us back to November 2022, when Wisconsin Department of Health Services declared those recommended enforcement standards. And this table is meant to do 2 things. So it shows you those PFAS substances that Wisconsin Department of Health Services recommended be regulated in water. And then it also shows you the concentration of those PFAS substances that were present in Eau Claire's finished water on July 6, 2021, when individual wells in the well field were tested, and 4 of those wells ended up being shut down because they did have elevated levels. So just looking at this, none of the concentrations of these PFAS chemicals were exceeded in the finished water at that time. And then looking ahead, just wanted to provide some information on average PFAS concentrations in Eau Claire finished water from June 2020 to April 5th, 2023. So that was just the last day of sampling that was included in this study. And then also maximum concentrations of PFAS for during that time period. And neither average or the maximum PFAS concentrations exceeded those WDHS standards. So looking at this list, there is an individual concentration in the parts per trillion range that has been established or recommended by the Wisconsin Department of Health Services. And then this list, PFOA and above, if WDHS is looking at the combined concentration of those PFAS substances, and it shouldn't exceed 20 parts per trillion. Okay, so now that we have a background, I'm going to introduce you to the methods that we use to approach this study. So we used a mathematical modeling approach to assess risk, and we were estimating the relative risk of adverse health effects in a population from exposure to hazardous agents. And in this case, it was these different PFAS compounds. So in any risk assessment, there are some steps that need to be followed. And these are the steps. So the first step is always identifying the hazard. So that in this case, the PFAS substances that were of concern. The second step is finding the toxicity information for those hazards. The third step is figuring out exposure information for the population of concern or individual, and then putting all that information together in a model and characterizing risk. So the first step was hazard identification. So we connected with the city of Eau Claire, and they provided a list of the PFAS compounds that they were analyzing in water samples from June 2020 to April 2023. So these are the 19 PFAS compounds that were of interest. So the next step in the risk assessment was searching the literature for reference doses for all 19 of those PFAS substances. Unfortunately, not all the PFAS substances have toxicity information available. So we were only able to find what's called a reference dose for 7 of these 19 PFAS compounds. And that reference dose is going to be used to calculate risk, which I'll explain when I talk about risk characterization. But before I do that, it's really helpful, I think, for those of you who are maybe not familiar with reference doses, just to understand where they come from. So I'll explain that quickly. So reference doses come from toxicity studies. Here's just a really basic image showing what might happen in a toxicity study. And obviously it might look a little different than this, but basically we're exposing a lab animal population to the chemical of concern. So in this case, those PFAS compounds or PFAS substances, we're waiting, and then we are observing a change in that animal, whether it's a change to organ tissue or a change to behavior, or maybe a change to development of a fetus if we're exposing pregnant mice, and we're observing that response. The definition of a reference dose is the daily oral dose of a non-carcinogen likely to not cause harm over a person's lifetime. I mentioned at the beginning of the talk that we were not assessing cancer risk in this study, and that's because we're using RFDs as part of our risk assessment, and they only assess non-cancer effects. So how exactly are RFDs calculated? This is a basic dose response curve. And we have on the y-axis, we always have response, which is just another way of saying, how did the animal react to that chemical exposure? Did they have organ dysfunction? Did they have behavioral effects? Was the fetus development affected? And at what dose did that response occur? So dose is always on the x-axis here. To calculate an RFD, you need something called a no observed adverse effect level, which is just the last dose that was administered by the scientists to the mouse population or whatever the animal is, where a response was not observed. So in my example here, the no observed adverse effect level is 20. So notice that this becomes important when we're interpreting risk and looking at risk assessment results. The no observed adverse effect level dose, there's no response that was observed in that animal population at that dose. To calculate an RFD, we divide the no observed adverse effect level by something called an uncertainty factor. And uncertainty factors we apply them because we want to account for the difference between mice and humans, or the differences between mice. So they might be different ages, they might be different genders, they might be different weights. And so we want to account for those differences. Usually uncertainty factors are equal to 10, but sometimes they might be equal to 3 or 7 or something like that. They're meant to provide a safety margin. So in this example, again, my no observed adverse effect level, where we're not even seeing a response, if we divide that by 10, our RFD would be equal to 2. So at a dose of 2, there's no response that's being observed in that animal population. So that their RFDs are protective, or they're meant to be protective. Okay, so I just went through hazard identification and dose response. The next step in risk assessment is exposure assessment. And in our risk assessment, we needed to find reliable values to insert into this equation, which calculates the average daily potential dose. And in this equation, the C is equal to the concentration of the individual PFAS compound of interest. Ingestion rate is IR, which is in liters per day. EF is exposure frequency. So how many days out of the year is our population exposed? Exposure duration, units are years. And then we need to know body weight, because for someone who's of a lower body weight, they're going to have more of a response. And then averaging time is equal to the exposure duration multiplied by 365 to convert from years to days. So to find reliable values to insert into this equation, we created a 4-question electronic exposure factor questionnaire using Qualtrics. And we wanted to be really thoughtful about our questions and what we were asking in those 4 questions, because we wanted to get reliable information. So we looked through the literature and we found some studies that had been published in the US EPA Exposure Factors Handbook, one of which was this study noted here that looked at the drinking water consumption in a day. And we used some images from that study so that we could help our participants report volumes that reflected what they were actually consuming every day. So both the survey and the survey distribution method both went through the institutional review board process, and they were approved in October 2022. So I'm going to share the 4 questions that we asked. We asked first, are you 18 years or older? If the respondents answered no, then they were taken to the end of the survey. So we excluded minors from taking the survey and from this study. If they answered yes, they were taken to the next question, which asked, how many fluid ounces of tap water do you consume in one day? Please don't include bottled water in your estimate. And we provided this image so that they could gauge how many large glasses of water they're drinking in one day, and then report that answer in fluid ounces. So not many of us think in fluid ounces. So this image was really helpful in having our participants accurately report what they're consuming, the volumes they're consuming in a day. The next question asked about, in a 1-year period, how many days do you drink water in Eau Claire, Wisconsin? We recognize that some people might be out of town on vacation or for work. So we wanted their answers to reflect that. And then we needed to know body weight. We asked in pounds and converted to kilograms later so that units would match up in our equation. So I'm going to turn it over to Alex Barker, my research assistant, who's going to explain the survey distribution method.
Okay, so with our survey distribution method, we had a survey that had the link to the survey itself along with a QR code for ease of access. This is distributed to Eau Claire's population from about November 2022 to March 2023. We did multiple neighborhoods that were canvassed, as you can see here in the different areas of blue. About 500 surveys were attached to the door frames as pictured above. The areas that we went to are mixed of both family homes and rental properties. We completed about 62 completed surveys with a 12.4 response rate.
Thanks so much, Alex. So after we had gathered that information, we could move on to risk characterization, where we put it all together and we came up with a relative risk number. So we input data from our exposure factor survey into this ADD equation and included that in an Excel spreadsheet that I'm going to share in a minute. We also needed to calculate a hazard quotient, and we did this for each PFAS substance. So those 7 PFAS substances that had reference doses, we were able to include in this risk assessment. A hazard quotient is equal to the average daily potential dose divided by the reference dose information that is available. And then the next step to characterize risk was calculating a hazard index. And in our study, the hazard index was equal to the sum of the hazard quotients. So taking the average potential daily dose of the first PFAS that had an RFD added to the ADD divided by the next RFD for the second PFAS, et cetera, for all 7 PFAS compounds. And the final value, the hazard index, this is an expression of relative risk. So this is what tells you about your risk. And in the case of our study, we're looking at the risk of the person's PFAS exposure, considering the exposure profile that they input to calculate ADD. divided by this RFD. So we're looking at risk relative to someone who's exposed to drinking water with concentrations of the PFAS compound that was established using an RFD. A hazard index that's much greater than 1 is a concern. If the hazard index is equal to 1, that means that the average daily potential dose is equal to the reference dose, because ADD divided by RFD is equal to 1. In that case, if both are equal values. And remember when I explained what an RFD is and how it's calculated, it is much lower than the no observed adverse effect level in a toxicity study where we actually didn't see any health effects in the animal population. So the farther we get away from 1, and really as we approach a much larger number than 1, then we start to be concerned from a public health perspective. So just to give you an example here, a hazard index of 10 would mean that that population is 10 times more likely to experience health effects compared to a population drinking water with PFAS at concentrations that were established by RFDs and considering the same exposure profile. If the hazard index is less than 1, there isn't a concern. And if it's much greater than 1, then that population or individual might consider reducing their aggregate exposures to PFAS. So exposures, not just to drinking water, but to all those consumer products that we might be using that contain PFAS. Okay, so we're still on risk characterization. So we put that model that I just shared was input into an Excel spreadsheet that can be used by the public, and that calculates a population or an individual, whoever's using it, their hazard index. So in the Excel spreadsheet that I'm going to share and that's available to the public, includes data from the exposure factor survey that Alex and my students distributed to community members in Eau Claire, the PFAS concentrations in finished water that were provided by the city of Eau Claire, those RFDs associated with the 7 PFAS compounds, and also a user manual to avoid a garbage in, garbage out situation so people can understand how to use the manual. So there are 3 tabs in the manual. The second tab we put together as a way for Eau Claire residents to calculate their hazard index and assess their risk in Eau Claire, Wisconsin. So the concentrations of the 7 PFAS compounds are fixed in that tab. So they can't be altered. So it's meant for Eau Claire residents only. But we wanted to extend the opportunity for others to use the spreadsheet and calculate risk. So the third tab is essentially the same spreadsheet as the second tab that's meant for Eau Claire residents, except users can manipulate the PFAS concentrations in that tab. So if anybody outside of Eau Claire knew the PFAS concentrations in a water source of interest, they could use this tab on the spreadsheet to calculate their hazard index. So with any risk assessment and any modeling approach, there are always assumptions. So I just want to be really clear about the assumptions of this model. So we could only find RFDs for these 7 PFAS substances. So the model only estimates relative risk for exposure to these 7 PFAS compounds. And we're only looking at a relative risk or a hazard index for drinking water. We didn't consider water that's used to cook food or water that's used for bathing or other purposes. We didn't consider PFAS exposure from other consumer products or industrial products, just drinking water. And risk is estimated from that user profile that's input by the person who's using the Excel spreadsheet. So it's going to look different depending on the exposure inputs that are inserted into the spreadsheet. For that, the second tab of the spreadsheet that I mentioned, we're calling it Hazard Index EC tab. This is the tab that calculates a hazard index for Eau Claire residents because those concentrations are fixed. The concentrations in that tab are the maximum concentrations that were collected during a 2.7-year period, June 2020 to April 2023. So they may have been only, those concentrations that are in the spreadsheet may have been found on one sampling day during that entire period of time. But in risk assessment, we usually look at the worst case scenarios. That's why those maximum numbers were inserted. The exposure duration is assumed to be 2.7 years because that was the time frame that we had PFAS concentration data from. On that third tab, which we're calling the Hazard Index Calculator tab, this is a spreadsheet where concentrations of the 7 PFAS compounds can be manipulated by the user, and therefore that tab on the spreadsheet can be used by people outside of Eau Claire, anyone who's interested in calculating their risk. And exposure variables in that tab of the spreadsheet can also be manipulated by the user. Other assumptions, like I already mentioned, the spreadsheet doesn't take cancer effects into account, so it's only looking at non-cancer effects because that's what RFDs are looking for. And because we excluded minors from taking the survey, the model only considers adults who are equal to or greater than the age of 18. So I'm going to share results of the exposure factor survey first, and then I'm going to share the spreadsheet. So from that survey that was issued to Eau Claire residents, here are results. So people reported on average drinking 1.7 liters of water per day, at a minimum 0.2 liters of water per day, and maximum amount of 5.9 liters of water per day. The exposure frequency average was 294 days per year, minimum was 3 days per year, and maximum was 365 days per year. And people reported an average weight of 174 pounds, minimum weight of 112 pounds, and a maximum weight of 290 pounds. We were curious if these data were an accurate estimate of these values. So we validated these results by comparing them to US EPA data from the United States population. And a lot of the numbers were pretty close. We felt like these were accurate values to input into the model. So looking at exposure data from the US population that was produced by the US EPA, we found that on average, the US population is drinking 0.711 liters of water per day, and the maximum ingestion is 2.6 liters of water per day. So Eau Claire is a little higher for both. Exposure frequency, maximum exposure frequency was the same reported in the US population, and weight was pretty much the same. Average weight in the US is 176, and the minimum weight was similar as well, 119 pounds. So I'm going to jump to the Excel tool. So I mentioned that there were 3 usable tabs, and the first tab is just named "How do I use this spreadsheet?" It is an overview of the purpose of the project. It goes over the model assumptions, so the same model assumptions that I just went through in the presentation. It provides instructions for the user on how to use the spreadsheet, and also some of those exposure inputs if someone's not quite sure what values they should put into the spreadsheet. It also provides instructions on how to use the drop-down menu on the tabs. So any box that's highlighted in yellow or any cell that's highlighted in yellow on the 2 tabs here can be changed by the user. This Hazard Index Calculator EC tab, this is the spreadsheet that is meant for Eau Claire residents because these values are fixed. So the user can't go in and change the concentration of PFBA, for example. It's going to be fixed in this case. But these exposure inputs can be changed. So if I knew that I didn't drink 5.9 liters of water per day, I drink less than that, I can click on the cell and click on this drop-down menu and scroll to something that reflects my ingestion. So maybe 3 liters of water per day. You'll notice that over here, when I click on this value, this number is going to change. This is the hazard index. So when I click that, my hazard index drops to 0.59. These cells this cell represents the reference dose associated with each PFAS compounds. This is the average daily potential dose based on the inputs up here. We change the units from pounds to kilograms in the equation, and we also account for averaging time. And then the hazard quotient is just the average daily potential dose divided by the hazard quotient, and the hazard index is equal to the sum of these hazard quotients. So like I mentioned, this hazard index calculator tab, this is the tab that's meant to be used by anyone outside of Eau Claire. And you notice right away that these cells are highlighted in yellow. So these can be manipulated by the user. If somebody is interested and knows the concentrations of PFBA and the other PFAS substances in a water source of interest, they can click on the cell and input those values up here. And then that's going to change the hazard index based on the concentrations that they input. And then the user is also able to use this drop-down menu to select an ingestion rate that and the other exposure variables that reflects their exposure. Okay, go back to the PowerPoint here. So I'm going to share some results of the risk assessment based on some different exposure profiles that we inserted. And first, just want to say that risk assessment sometimes is used to develop policies. And when we do that, we usually consider the worst case scenario, because if you're considering the worst case scenario, you are protecting members of the population who are the most vulnerable and everybody else in the population. So the following scenarios are worst case scenarios, and they're also hypothetical. So they didn't actually occur in Eau Claire, Wisconsin, but we tend to look at these worst case scenarios to make decisions about what's healthy for the population. So here's the first scenario that I'm going to share. And an individual with the exposure profile that I use for this first exposure scenario assumes that they're exposed to the maximum concentration of these PFAS substances every single day, again, which never actually occurred. So that assumes that between June 2020 and April 2023, the maximum concentration for those 7 PFAS compounds occurred every time that the water was sampled, but it really only happened one time. The scenario also assumes an exposure duration of 7.2 years, 2.7 years, and then this maximum ingestion number. So we're assuming in the scenario that I'm presenting that the person was drinking 5.9 liters of water per day during that period, maximum exposure frequency of 365 days per year, and then a minimum weight, because the less you weigh, the more affected you are by the compound. So 112 pounds. And again, that maximum PFAS concentration for each of those 7 PFAS compounds in Eau Claire's finished water. And that gives us a hazard index of 1.16. So I'm going to change the numbers around just slightly. So we might look at this scenario and say, well, let's reduce the ingestion rate from 5.9 liters of water per day to 1.7, because that was the average ingestion rate. And maybe that reflects an ingestion rate that for more of the population. When we make that simple adjustment, so this is the same person or group of people who weigh 112 pounds, same exposure frequency of 365 days per year. Everything else is the same, except we changed maximum ingestion to average. We come up with a hazard index of 0.33. And then when we just change the weight, so we insert the average weight that was reported on our exposure factor questionnaire, keep everything else the same, we come up with a hazard index of 0.71. And then when we make many more changes and we assume average for everything, so average ingestion, average exposure frequency, average weight, and then average PFAS concentrations in Eau Claire's finished water, which the values that were inserted into the spreadsheet to get this hazard index are all on the table here. The hazard index is 0.06, so very small with those values. So what does this all mean? So for any risk assessment and modeling approach that you take, choosing the inputs, it can be really tricky because there are limitations with all of the inputs that I just shared with you. So for our hazard index was 1.16 for that hypothetical worst case scenario that I presented. And there are, of course, some limitations for this. So this assumes, again, those maximum PFAS concentrations occurred every single day during that June 2020 to April 2023 period. And it also only looks at a certain very small portion of the population. So looking at our bell curve associated with body weight, people who weigh 112 pounds or less, that hazard index will apply to them, but that's a really small portion of the population. And same thing with people who are drinking 5.9 liters of water per day. So if we were to look at a bell curve for water ingestion rates, they would be on this upper end, and that would exclude anyone who never drank that high volume of water every day. And then when we change the average ingestion rate, so we change it from 5.9 to 1.7 liters of water per day, our hazard index changed drastically. It dropped to 0.33 from 1.16. So that might be a more realistic scenario for some people. And then when we looked at the hazard index for the worst case scenario, but just changed one thing, we changed the body weight to be representative of the average body weight that was reported on the exposure factor survey. We found a hazard index of 0.71. And that average weight is going to represent more of the population. So everyone 174 pounds and above. So this might make more sense to some people, but there are limitations associated with this scenario. We're still assuming maximum PFAS observations, and we're still assuming maximum water ingestion rates. And then the exposure profile that fits most of the population, when we assume average body weight, average ingestion rates, and average exposure frequency, combined with those average PFAS concentrations found in Eau Claire's drinking water over that 2.7-year period, our hazard index was 0.06. But this excludes individuals who have lower body weight, who are drinking a lot of water and are drinking 5.9 liters of water per day, and people with high exposure frequencies. So I think the takeaway from the exposure profile scenarios that I just presented is really that they're all pretty low. And when you look at the concentrations of the 7 PFAS compounds that were included in this risk assessment relative to the Wisconsin Department of Health Services recommended enforcement standards, all of them were lower than those recommended standards, but a lot of them were much, much lower. So these levels in Eau Claire's finished water the concentrations are driving low hazard, are driving these low hazard indexes and low hazard quotients. And that is, that means that in Eau Claire, Wisconsin, because of these low concentrations, it seems like the public is not being exposed to a amount that's of concern. If someone uses the spreadsheet and they are concerned, then we have some recommendations for them. And these are some options for reducing PFAS exposure. So using an alternate water source. So if someone uses a spreadsheet and they come up with a higher hazard index that's much greater than 1, then they may consider using a different water source for drinking, but also cooking and brushing teeth and any time that you might be ingesting that water. And then for those people who may be having PFAS exposure from local game or fish that they are hunting, they can check local advisories to make sure they're not ingesting PFAS or excess PFAS through those routes. Contacting the Consumer Product Safety Commission, and they can provide information on the consumer products that you might be using that contain PFAS. So here's their phone number. They also have a great website. And then also considering people who have exposures to PFAS through their work. Chemical manufacturers, firefighters, and ski whack technicians tend to have higher exposures to PFAS than those of us who don't work in those occupations. So consulting with supervisors and then following American Conference of Governmental Industrial Hygienists exposure guidelines. So in the future, I know at the beginning of the presentation, I mentioned that the US EPA has announced that they are planning to propose some maximum contaminant levels for 6 PFAS compounds and add them to the National Primary Drinking Water Regulations list. So just as kind of in the future slide, I wanted to look at just one date and time, the concentrations of those 6 PFAS compounds that the EPA is proposing MCLs for, and see what's ahead for the city of Eau Claire. So I just chose one date, the last date of data that was provided to us, April 5th, 2023. And I looked at PFOA that was analyzed, or the concentration that was found on that day, which was 1.16. US EPA is proposing a maximum contaminant level for PFOA of 4. So on that day, City of Eau Claire and their finished water did not exceed that MCL. That might be in the future. It's not an MCL quite yet. And then for PFOS, 4.6 in Eau Claire on that day, and the MCL for that is 4.0. For the other PFAS compounds, the 4 remaining PFAS compounds that the US EPA has proposed creating an MCL for, it gets a little more complicated. It's not just a concentration that they're looking for. It is a combination of ratios. So they're also using a hazard index approach. So what this table is showing is what the EPA is calling the health-based water concentration levels in parts per trillion. So for PFNA, it's 10, for Gen X, it's 10, for PFBS, it's 2000, and PFHXS is 9. And then in this column, we have concentration of PFAS in these PFAS compounds in Eau Claire finished water on April 5th, 2023. And then the EPA is having the municipality calculate a hazard quotient, which is equal to the concentration they found in their water divided by that health-based water concentration. So that is equal to the hazard quotient right here. So 0.0022 is 3.8 divided by 2000, and 1.5 is 14 divided by 9. And then the EPA is going to have the municipalities add all of those hazard quotients together for a final hazard index. So on this day, April 5th, 2023, in the future, the hazard index would have been 1.5.022 for the city of Eau Claire. So the US EPA is going to look at the running annual average of those hazard indexes that are calculated every time a sample is taken. So if the annual average the running annual average of those hazard indexes was greater than 1, then the municipality would be in violation of the maximum contaminant level. I want to acknowledge a few groups and people before I take questions. The City of Eau Claire Utilities Department for providing the PFAS concentration data. Richard Falk with the Council for the Model Aquatic Health Code for helping with the spreadsheet, as well as Crispin Pierce with the University of Wisconsin Eau Claire. And then special thanks to all the survey participants from Eau Claire, Wisconsin, who took the survey and provided information on their drinking water exposures. So this time I can take questions.
All right, that was great. Thank you. We've got some questions in the Q&A, and I'll start reading them. And for others, if you have your questions, please post them now. We'll have a few minutes to discuss with our guest here. So one of the questions is about the HI, the hazard index calculator. And it says, it notes that there's new data from EPA. So it's asking if you're using that new data or if you're using the Department of Health Services recommended data that was their recommendation was based on. So this one is noting that there are substantial differences between the two for the 6 substances you just outlined.
Yeah, so the spreadsheet does not use any of the maximum contaminant levels. So it is just using reference doses, and it's using that exposure factor information that came from the questionnaire along with the concentrations that were provided by the city of Eau Claire.
So do you think that the spreadsheet needs to be updated with any new information from EPA?
It doesn't include any information from EPA in the spreadsheet. So the new values that the EPA has proposed some maximum contaminant levels for some of the PFAS compounds other than the 7 that we did identify RFDs for, but they were established using something called minimum exposure levels, so they weren't included in the spreadsheet. So in the future, as more RFDs come out, then more PFAS compounds can be added to this spreadsheet, which I think will be really good because it will be more comprehensive assessment. But at this time, until we have those RFDs, then we can't calculate the hazard quotients for those PFAS compounds.
Okay, great. So another question from the audience, do we know anything about the cumulative effects of PFAS in the human body?
Yeah, that's such a good question. So as I mentioned, we're all exposed to these from many different sources in our daily lives, probably every day, unfortunately. And that was beyond the scope of this study. And that is part of what the EPA is working on, trying to understand those aggregate exposures and how they build up in our bodies and how that affects our health over time, and how that affects the growth of fetuses for pregnant women, and all of those questions that we have.
Thanks. We have a few more questions. I just want to also draw people's attention to the chat. There's a link to a policy brief that the Center for Water Policy just released this week that gives the regulatory context for this discussion today, and a link to EPA. There's a public comment period on the proposed new maximum contaminant levels that's open for another month or so, and then the EPA will be finalizing their rule, expected to be finalized by the end of 2023. So you can get more information on that through the link in the chat. Okay, another question here. Let's see, current assumptions are based on 2.7 years of exposure. However, have you considered what the hypothetical hazard index values and ranges would be if that period were extended to 10, 15, 20 or more years?
Yeah, so that reference dose is equal to the daily oral dose of a non-carcinogen, and then the average daily potential dose is a daily dose. And so because we're dividing exposure duration by averaging time, we actually end up canceling that exposure duration out. So because we're just looking at that daily dose, the hazard index doesn't change based on exposure duration. So when we're considering cancerous effects, that's when we're looking at that lifetime exposure. So because the spreadsheet and the model doesn't account for that, then that again is beyond the scope of what we're doing in this study.
So to assess cancer risk, you would need a different model.
Yes.
To highlight the limitations of this study. All right, great. Let's see. One more question here. Do you know if anyone has attempted to calculate risk factors based on various exposure pathways on top of drinking water? Such as
from those aggregate exposures. I do not off the top of my head, but I can see where that would become really complicated since we are exposed in many ways. But I think that's a great future project, and I'd like to see that be completed if it hasn't already, because I think that would be really useful for the public in assessing risk and then trying to make those really tough decisions about the types of consumer products that they're using and what they can stop using or what they might minimize to kind of control the amount of these substances that are getting into their bodies.
Thank you. Let's see, do you know if studies like this are being performed for other recreational sites in Wisconsin? Also, if there are other agricultural centers in Wisconsin that are doing this kind of evaluation?
I did not come across anything in my research. I know that there are some different uses of the hazard index that are occurring, but I'm not aware of anyone or any groups that are looking at the kind of the exposure profile of a population and then trying to assess risk based on whatever PFAS compounds they may be exposed to. But I think that this type of model and tool can easily be manipulated for any scenario as long as you have the inputs that are needed to calculate the average potential daily dose, and then if you have the RFDs for those compounds. So it definitely can be used in other settings.
Thanks. There's a question about calculating risk values for the entire state. Is that something that this model could be used for, or does it really have to be done on the local municipality level?
I think it could be done for the entire state. So if there was a survey that was broadcasted to a larger audience, people all throughout Wisconsin could gather information and insert those values into that ADD equation, and that would estimate risk for the entire population of Wisconsin.
All right. Well, with that, I think we'll close out the webinar. Thanks for being a wonderful guest for us today and such a great water scholar for us all year. And it's been fantastic to get to see how your project has evolved since you started it. And thanks to our audience for sticking with us and for giving us such great questions throughout this event. So with that, I want to give you a round of applause. And I know our virtual audience is joining in. So thank you.
Thank you, everyone, for joining. Thanks, Melissa.